Hey everyone. So today we were continuing uh, on to week 6 for the recurrent neural networks from the syllabus, and we had looked at how other neural network architectures can be useful for basically optimizing a model, trying to understand and build these models that can actually predict data. So one of the hard things about science is that a lot of times we don't know the model that we're trying to fit, right? Um, and so if we are given data, the problem with that given data is that um, we don't always know what the model should actually look like. Does it look like the data, or is there signal and noise in the data that shouldn't be there in the actual model? And there's a lot of work that goes into trying to what people will call fine tune a model. And that is where they can take a model and try to get that model to be as precise as it possibly can, and to be able to answer just about every possible uh, question that it could be asked correctly. There's a problem to that, though. The problem is just simple physics. Neural networks have a memory capacity. And that means that, well, think about it this way. If machine learning could learn anything, then that means that the laws of quantum mechanics aren't correct, and the laws of thermodynamics, right? Because quantum mechanics says we can't describe everything with exact precision. So in order to basically come to this idea of how can you avoid basically optimizing the model to fit everything, is you don't, right? So what we're going to show is we're going to show that there's actually a better way. And so at the end of this lecture, you'll be able to explain that hyperparameterization results in basically just pure route memorization, not actual intuition as to what something is trying to trying to basically model. And you'll be able to demonstrate the difference between a recurrent and a forward neural network. And you will also be able to, in your own way, show or prove that error is not a valid predictor of predictability. And you'll also be able to explain how Boltzmann, the mean free path that you studied in your intro physics course, actually relates to better modeling and when you actually use physics inspired. Well, I not physics inspired, but actually use proper fitting techniques. So, and how to avoid this hyperparameterization. So the first thing that basically, again, like we just talked about, what are the objectives? Basically, as we talked about, you're going to have an overfit for bad data, but you want something that's actually a better fit, and again, demonstrate the difference between the neural networks types, and also talk about error. So if you recall in the prior lectures, curve fitting, you start off with loading the data, you get a measure of the data compared to some basis functions, And you calculate the difference, and you basically get a curve fit from that, right? So you iteratively move towards having a better fit. So if you recall, we have our original program here that you guys will have access to this, and during the lecture you'll be able to interact with this to answer a few questions, and actually there's going to be a breakout group at some point that we're going to have everybody sort of work and collaborate on. Basically, this is what you are going to work through today. So what you're going to see is that you have this program here that all the code is already done for you. You just basically hit the run button, and I think I have to start this over. So basically you're going to hit the run button, and you see that the neural network automatically fits itself. And this is a normal forward neural network. So, and all we're doing here, again, is basically, there's a lot of code here for the graphics and drawing, but you'll have the prior notes that basically all we're doing here, if I can just find where that went, it got hidden. Basically, we're just using your physics computations to calculate a velocity based on the error. So rather than it being potential energy, we just replace potential energy with error. That's it. Everything else stays the same. So, same as in physics. So we run the simulation and we get a fit, the error goes down to 0. And the curve here I have is a Gaussian. So we can already start to see that there's an immediate issue here, that it's the actual network is not fitting the actual curve. Now, how can we fix that? Well, we could tune hyperparameters, or the other thing that we can do is we can come down here, and if we were really lucky with our experiment, I can set the noise here under the Gaussian function and run it, and there's still some noise there. Yeah, sorry. Basically, you can get a chance to work this out on your own, but basically, you should be able to have like zero error. Yeah. So if you didn't have any noise, you would get a much better fit. And this is what I get for asking Gemini to debug my code for me at the last moment. Calculate the true signal. Oh, so that's the true signal. Okay, so somewhere here it here it is. Okay, so basically all I did was I needed to find out where it was actually calculating the noisy signal. And so if we run this, you can actually see that the noise went to 0 because it's exactly fitting. So now if I run, we get a perfect Gaussian, right? So now there's no problem, right? So, and we can turn up the number of nodes, no problem. But let me put the noise back. And now if I increase the number of nodes, the error is still 0, but you can see that it's actually fitting the curve worse. So what I'm going to let you guys do is for the breakout time is going to pause right here, let you guys work out for a couple minutes where I'll put up a new function on the board that's going to replace your sine function, and you're going to basically put in that function, and then I want you to do the same thing that I just did to see if the neural network, by increasing or decreasing the error, does that help? So I'll let you guys get to work for a couple of minutes, and we'll join back up in just a moment. Okay, so basically you guys got to see that there was no well, that the error basically goes to 0, but yet it's still not a good fit, even for when you're working with especially something like a sine wave or a multimodal Gaussian, like you got to see in your breakouts. So if there's no further questions, we'll move on to the other approach. So what this other approach is basically, think of this. If when you're fitting your Gaussian, you have these nodes and you're going from node to node and you're looking at all the data points, rather than sticking the nodes at a specific data point and trying to get all the nodes to fit every single data point, what if we looked at how many data points, the space between the nodes, that ray vector, how many points that goes through? And when you do that, you basically have two outcomes. Either the ray goes through the points or it doesn't. And if you remember from your statistics, what does that lead to? Anybody remember? Yes, exactly, the binomial distribution. So if you recall some of the where the Boltzmann distribution for gas and mean free path, they're linked, right? So we can discuss that in a little bit more in the next class. But basically, you will have a set of successive trials, and over time you look at how accurate or not accurate a given trial was, and as you do that, you basically accumulate a history, sort of like a latent space, a latent memory, your history disguised into the prior math, and we'll go a little bit more deeper into this for the later on in the session today. So basically, if you do this, it gets you a better approach. So again, all we're doing is we're just basically connecting lines, drawing little line segments piece by piece to build up our curve. But again, we're going to use physics, so we're going to use information from the past time. So we're not just fitting every node now, we're actually fitting nodes adjacent to the past nodes. So when you do this, so here again, this is a different program that this is going to demonstrate how this works in the homework assignment, you will basically be taking this code and adapting it to this. And the only thing is different is that you're just averaging the nearby points. That's all that you're really going to do. So rather than just looking at the actual error, you're going to look at the sort of average error around each node with a little bit of a multiplication. We will, and again, that formula will be in the assignment for the homework. So we'll straight up give you that formula, so you won't have to derive that or anything. So now when we run this for the mean square, we can see how it behaves. But then if we look at this new method and we run this, we can see that now the signal is getting much closer to the ground truth. If I increase the number of nodes now, it's a better fit. It gets rid of the noise. Expectation values, right? Expectation values are the key. You want the expected outcome, not a given. Don't expect a given outcome. You're looking for the expectation value. So, and again, the only difference is that basically we're just looking at the average points and treating it like a particle diffusing through a gas. So does this look at all familiar? And you should remember your transfer matrix equations, and I'll have to double check this equation, but basically your Snell's law, right? That the angle incident and the angle reflected, all of that you worked out in your intro physics. Well, here's the thing. The equation that you just did, we just talked about it being a series of successive lines, right? So it should look just like your transfer matrix for thin films. And so next week, we're going to look at how can you take a bunch of glass beads for a bookend and shine a laser through it and get an exponential curve. It's exactly the same math that we just did. And then on top of that, you guys will be able to relate that to the pixels that you see on your screen, because that's just very much smaller glass that's very similar to the bookend that we'll look at next week. Thanks.